Hello, bonjour, Chiara. I'm Adrian. It's June 6th, and this is AInVFX News. I'm so excited about today's episode. We're going to be covering 4 game-changing research papers that are really pushing our direction in video diffusion models. NormalCrafter for relighting, Any-to-Bokeh for depth control, Uni3C for camera and human motion, and finally ATI to draw any kind of trajectory and watch them come to life. Now, today is really special because we're going to do a deep dive into ComfyUI, so I'm going to show you how to art direct every aspect of your generation. All the workflows are included in the description. You're in for a treat, so grab your coffee, sit back, relax, and let's do this. Let's look at an interesting paper released mid-April that has now been implemented in ComfyUI, NormalCrafter. This is a video diffusion model that estimates surface normals from RGB video. Surface normals tells us the 3D orientation of surfaces, essentially which direction each point is facing. They are useful for scene relighting and can also serve as input preprocessor in VACE to control new generations. Previous methods estimate normals frame by frame, causing flickering artifacts. NormalCrafter solves this by leveraging the temporal consistency of video diffusion models. The key innovation is semantic feature regularization, or SFR. This technique aligns the diffusion feature with semantic representation from a Dino encoder. What does this mean? It forces the model to focus on the actual meaning and structure of objects, not just surface textures. The training uses a clever 2-stage approach. First, they train the entire unit in latent space using diffusion score matching and their SFR loss. This establishes the basic normal estimation capability. Second, they fine-tune only the spatial layer in pixel space. They switch to an angular loss here, which directly measures normal accuracy. This preserves spatial precision while keeping the temporal consistency from stage 1. The code is available on GitHub with MIT license and the model on Hugging Face with Apache 2 license. AI Warper created a wrapper for ComfyUI last month, so let's dive into it now. In ComfyUI, if you have not installed it before, you go into the Manager, Custom Node Manager, and you're going to be looking for our NormalCrafter. Here it is. And another node pack we're going to be using for this demo will be the Video Helper Suite, so make sure you have it installed. Once those two are loaded, let's start with some footage. I'm gonna grab a basketball footage from Pixel that I will add in the video description if you want to play with the same one. For now, I'm only going to be loading 1 frame just to keep it simple and easy. Let's grab our NormalCrafter. Image goes into image. Ignore the pipe override for now, it is not implemented. Then we're going to go into our preview image and we're going to run the workflow as is. If this is the first time that you are running this node, it's going to download the model, so be patient, but after that it should be reasonably fast to run. Now that I have some issue with my hardware at the moment, and there's some incompatibility, I suspect it's my hardware instead of the code, but just to avoid the very verbose log output, I'm going to disable the offload pipe to CPU and finish. If that thing works for you, the idea is that when the processing is done, we're going to offload everything onto the CPU to free up some GPU VRAM. It's a bit slower, and that means that the next time the node is going to rerun, it's going to have to offload and bring it back onto the GPU, but it's going to save some VRAM if you are low on resources. Okay, here we have our output, which is pretty good overall, but as you can see, it does miss some of the high frequency details. So we can now, in addition to this, add a detail transfer. So we're going to go image into target, and our source is going to be our original footage. And then we're going to let's compare with another preview, and we're going to rerun that. So now, as this detail transfer node is going to inspect our input footage, and you have multiple mode here. Here I'm using add at the moment, and it's going to bring back some of those high frequency details. we start picking up some of the details of the grass, more details in the tree, and on the character as well. One setting that you can play with here that would be the blend factor. If you think that you like the details, but it's just a bit too sharp, like you can bring that blend factor down to like a 0.5 or something to bring it down a bit overall. Okay, now if we want to play with video, let's bring back some animation here. So I'm gonna take my frame load cap to 20, so I see a bit of something, and I'm going to cheat my FPS. I'm gonna put it at 8 because I want to see a bit more variation in my input footage without having to process too many frames. Now let's delete those preview images. Instead, we're going to add a video combine because we're going to be working with video. Because I'm lazy, I'm going to use a video info node and go video info to video info and grab the loaded FPS into FPS. This way, whatever the FPS value I have in my loader is going to be the same in my output. Gonna change my prefix, NormalCrafter, set the format to MP4, and we are going to run that. While this is running, let's talk about the settings. Here we have a max res dimension, so it's going to look at both the width and the height and ensure that they're both below 1024 before processing, otherwise it's going to scale them down. The window size, it's to ensure that we don't run out of GPU memory. So if you imagine you have a video with a lot of frames, in my case I have 20 frames that I'm processing, I'm now only going to be processing 14 frames at once. Okay, so the higher that number, the more frames are going to be processed at once. So the more consistent it's going to be temporarily, but it's also going to require more VRAM. Below we have the time step size, and that means that each time the NormalCrafter is starting its processing, it's going to increase by this number of frames. So we're going to process 14 frames at once, and once 14 frames are done, we're going to be increasing 10 frames, and then process 14 frames, then increase 10 frames, and process 14 frames, and so forth. What that means is that for each batch of 14 frames, 4 of those frames are going to be overlapping with the batch from before and the batch from after. Why we want to have this overlap is to ensure that when we look at the entire sequence, which will have likely more than 14 frames, we don't see some jump, some inconsistency each time there is a new batch popping. Okay, so you can play with those two values. Again, you can increase them if you have a lot of GPU VRAM. However, we want to make sure that the time step size remain below the window size, because we always want to preserve some overlap between each window of frames to ensure we have a smooth transition between each batch. The decode chunk size is for the VAE, so if you are running into memory issues, you can bring that number down to 2 or even 1 if you just want to process 1 frame at a time. Okay, let's look at the output now. You can see it's pretty good overall. It's not perfect. There's a bit of flicker in the background, and to be fair, it's quite hard to get rid of it entirely. But it's pretty good overall on the character. You could try, as we say, like you could try to increase that, let's say to 28, and now we're gonna have like double the amount of frame in each batch. And I would increase that as well, the step size maybe to 20, and this way we have 8 frame overlap between each window size. There you go. It's slightly better. Again, it's not perfect, but compared to other solutions out there, it's still pretty good. give it a go. You can use that for relighting. You can feed that into DaVinci Resolve or any other compositing software that you like using, or you can also feed that into a vase if you want to use as a preprocessor. The workflow is available in the description below this video. Have a play and let us know what you think. Thank you very much. Let's move to a promising research paper released last week, Any-to-Bokeh. This is a one-step video bokeh framework that adds realistic depth of field effects to any video. Unlike previous methods that process each frame separately, this system maintains consistency across the entire video sequence. The key innovation is their use of multiplane images, or MPI. Think of MPI as slicing your scene into multiple layers at different depths. Each layer represents objects at a specific distance from the camera. This gives the model explicit geometric guidance about what should be blurred and by how much. You get two main controls here. First, you can choose what to focus, and second, you can adjust the brush strands, which simulates different apertures. You can animate both controls to create professional focus pull effects. So how does it work? They built on top of Stable Video Diffusion, adding custom MPI special blocks. These blocks use attention mechanism to process different depth regions separately. Cross-attention helps preserve important visual details. Their training strategy has 3 stages. First, they train the entire network with adapters. Second, they refine the temporal blocks by adding noise disturbances to improve consistency between frames. And finally, they fine-tune the VA decoder to preserve fine details. By combining the video diffusion model's built-in understanding of motion with the MPI depth guidance, this method achieves smooth, stable bokeh effects. The code is not available yet, but they intend to release it soon with testing files, training, and pre-trained weight. So watch this space. Let's explore Uni3C, a paper released 2 weeks ago that enables art direction of camera motion and human motion in video diffusion model. This is a unified framework for both camera movement and human motion. Previous method handled this separately, but Uni3C brings them together in a single system. What's impressive is that it doesn't require joint training. Each component can be trained independently. The key innovation here is PCD Controller. It's a plug-and-play module that uses point clouds for precise camera control. Point clouds are 3D representations of the scene extracted from monocloud depth, like how your brain judges distance with one eye closed. What's clever is that PCD Controller doesn't modify the video generation model itself. The base model, like Stable Video Diffusion, stays frozen. You only train a lightweight control net for camera and human motion that plugged into the model at inference time. The system uses a smart alignment process. First, they position detailed 3D human models, called SMPLX characters, within the environment's point clouds. They use GeoCalib, a tool that calibrates gravity direction to ensure people stand upright naturally. And then they render everything under specific camera trajectories to create unified control signals. The code and model are available with Apache 2 license. The great Kijai has already integrated it into ComfyUI as part of the One Video wrapper. So let's take it for a spin, shall we? Please go into the manager and make sure you have the last version of the ComfyUI One Video wrapper from Kijai. You can try to update it if you haven't done that today. You also need to make sure you have the Kijai notes pack, which is this one, and we lastly are going to be using the Video Helper Suite note pack. So make sure you have those 3 packs installed before starting that tutorial. Once you have all of those, you can load the example workflow for Uni3C that is included in the comment in the description of that video. So this is a traditional 1.2.1 image to video workflow where I've added in yellow here the Uni3C control net and the input for the control net. Other than that, we have the section here that takes care about our model. If you are missing any model file, you can download everything from Hugging Face at that link. Note that I'm using the 14B version of the image to video model from 1.1 and the 720p resolution. I'm also using the Cosvid LoRa as a way to speed up the generation. You might not want to use that for production, but when we are iterating, it's a great way to ensure the generation time is kept quite low. I'm using Torch Compile and Block Swap, but that's specific to my own hardware and Linux environment. So if that doesn't work for you, feel free to tweak them accordingly. Whatever you need to do to keep your GPU VRAM consumption under control and make sure that your generation time is not too slow. Here I have the text encoder and the prompt. Note that at the moment I'm not using any positive prompt at all, but I will get back to that in a second. I do have the sampler. It's set on step 5, and that's only because I'm using Cosvid, so I can get away with such a lower step number. The CFG is set to 1, that's important, and the shift is set to 7 to allow for bigger camera motion. We all like a 42 as a seed, so I'm keeping 42 here, and the scheduler is set to UniPC. Other than that, in terms of the input, I'm using waterfall and river picture from Pexel, and you can find it in the description of the video if you want to use the same for testing. I'm resizing it to 512, and that's only to ensure that my iterations are quite fast. But feel free to disable that node if you don't want it. Then it goes into the traditional image to video encode node with the clip vision to make sure that we have the pixel data and also the meaning of the pixel data that is embedded before going into the sampler. At the bottom here, I do have my input for Uni3C and the control net here. In this tutorial, I'm only going to be focusing on camera motion. Uni3C is able to deal with camera motion and human motion, but I found that the results were not as amazing as I was hoping for with the humans, so I'm only going to be talking about camera motion for now. Here you can set your control net, so use the Uni3C control net. If you don't have it, make sure you download it from the Hugging Face link, which is here. And then you put it into your ComfyUI folder under models/control net. We then have here the setting for that control net. We're going to be able to play with the strength, so how much of an influence we want the control net to have on the generation. We can go to value up to 2 or 3, but if you try to go higher than that, you're going to run into artifacts, so don't try to push it too far. Then we have the start percent and the end percent. That's to control where within the diffusion stages we want the control net to take effect. So at the moment we have 0 to 1, which means it's going to take effect through the entire diffusion process. Keep in mind that at the beginning of the diffusion process, we are only working on large-scale features. At the end of the diffusion process, we're refining high-frequency details. Because here I'm trying to affect the camera motion, either I'm going to apply it through the entire diffusion stage, so from 0 to 1, or I might just focus on the earlier stages using a value around 0.25. Lower values will make sure we only affect the early stages of the diffusion process when the largest features are being created. And then we're going to let the model free to generate high-frequency details from there. By doing so, we should get a result that is more organic, believable, maybe less constrained. Okay, before I go into too much details, I'm going to render a default generation without Uni3C, just so I have a ground truth that I can use to compare when I'm going to start playing with Uni3C. I'm not going to make you wait for the generation, even if they're pretty fast. They'll be under 2 minutes, but for the sake of time, I'm going to speed up the video. So I'll see you in a second. So it's been just under 2 minutes. Image has been resized to 512 by 512, and then we get our render here. It's pretty nice. As you see, the quality is definitely not perfect, but that's fine enough for that testing. once we go into production, we can turn off cause vid and increase the number of steps here. Let's add some camera motion into that. So the way we're going to do it, we're going to re-enable those two groups here. So set group node to always and set group node to always. You can technically use any type of video as input as long as there is some kind of a camera motion. Because I'm a bit lazy and I want something that is going to be interactive, what I'm doing is I'm going to use a load 3D node that's going to allow me to load a 3D model. I've created a cube that's here that I will add into the description if you need it. With this cube, we're going to have the ability to move the camera around it, and then we're going to feed that as an input to Uni3C, and that's going to help guide our diffusion process. So let's give it a go. We are going to start with framing. That's arbitrary, pick whatever you like. I'm going to press on that camera button here, and then I'm going to move around my cube, and then I'm going to stop the recording. Now, what's happening with that recording? So if I just disable, let's turn off that preview here, so I can show you the output of it. If I run the workflow now. So what you see is the input video here. Okay, so that's just what we recorded. What we have here is that we have the load 3D node that goes into the get video component. So we capture the images that we've recorded in that 3D viewport. Then we resize it and we make sure that it is the same resolution as our input image here. So the Boss 512, which is great. Then I have an image from batch node, and that's just a sanity check for me to ensure that my sequence is not longer than 81 frames. So the 81 frame is the limitation from 1 in terms of how long this video can be, and the model works better at 81 frame as well. So I'm going to limit it to no more than 81 frame. Here at the top, I'm going to capture that frame count here, and I'm going to feed that into my num frame of the image to video encode node. Okay, let's say if I were to do a faster camera motion, that was just 2 seconds, I will end up with less frame, and I will make sure that the video that we're going to be generating here with that sampler is going to be matching exactly the amount of frames that we had in my input camera motion. If there is more than 81 frames that input camera motion, it's going to be clamped at 81 frames by that node. Okay. So once we have that camera motion, we need to encode it. So we are using the VIE that's here. We encode that into latent space, and we're going to feed that into our control net. So here we grab the control net. The control net is taking the compile args as an input, which is the same torch compile that goes into the one model. You don't need to use that. I'm only using it with my hardware because it is faster, but it is incompatible for you. You are welcome to disconnect it. From here, we go into the Uni3C embeds from the sampler, and we are going to start seeing some generation. So I'm going to reconnect that node here, which is going to do a nice comparison. And as one input, we're going to see our input image, the input motion, and the output video. So let me enable that again, and I'm going to render a new sequence. I've duplicated the generation from before, so we can have it as reference. And now what you can see is that we have our input frame, the motion input, and then the result output here. Okay, that's pretty nice in terms of the motion. A few things we can tweak from there. So let me duplicate that again so we can have it as reference. We can come here and we can try to increase the strength of the control net. Now what's happening? We've seen that the strengths have been increased, but as a downside, our water is not moving anymore, which is slightly annoying. You could reduce the strength if you wanted to, but let's try to push a bit further to see if we can make it work with that amount of strength. Let's say if you really like the camera motion, but you want to make sure that you preserve your flowing water. One thing you can try, oh, there's more than one thing, but we're going to start with one. Duplicate that again. We are going now to reduce that n%. Remember, I said that number affected when the camera motion, when the control net was going to affect the diffusion process. Because we only technically need it for the large scale feature, we don't need it for the fine details, like the detail of the water flowing, we can focus it only at the beginning of the diffusion process. So let's go with that and see where we land. And now you can see that some of the water, most of the water, is back in terms of motion, and we do preserve the new camera input as well. Another thing you could have done, if that was not enough, you can also start prompting. Remember that at the moment we are not using that here. At the moment, we are not using any prompting at all, okay? We are only relying on the clip vision that is here and the input image. But you could definitely use prompting as a way to correct what the model is not doing well. So you could say fast flowing river. And if I run that, that should start bringing back some of the motion as well. And now you can see that the water is definitely flowing way faster than before. Like if we compare this to here, there's more activity here there. Okay, one last thing to remember is that this is seed dependent. So all those generations have been done with the same seed to ensure we can see what's happening when we change our settings. But if you're not happy with what you get with one seed, you're more than welcome to use another one and run it again. So as you see now, if we compare that, like just by changing the seed, the result is quite different. I will highly encourage you to try to set the seed early on in the process, because it's going to affect quite a lot the look of the generation. So try to pick a seed that you like early on in the process, and then you can start refining from there. One thing to remember as well is that, especially if we go back to one of the first generation, where it's the most obvious, you can see that the camera motion is happening before the cube starts moving. And that was when we were using the influence of 1. When we went to the influence of 2, the camera motion is still starting a bit early, but it's way more connected to the actual cube. It is a trade-off because those models are trying to do something that looks nice, that looks realistic, while at the same time being controlled by the control net. So you need to figure out how much you want to be very strict with your input, like how much influence you want your input to have, while still ensuring you have a nice, pleasing, physically accurate output as a result. So there is no perfect number. You definitely need to play with all of those values, but I'm hopeful that by showing you how those values impact the generation, and keep in mind that all those renders were reasonably fast, like under 2 minutes. So do not hesitate to play with the settings, see what you get until you find something that works well with what you're trying to achieve. You'll find the complete workflow available in the description. Have a play with it. Let us know what you think, and I'm looking forward to seeing all your results. Thank you very much. I've saved the best for the end. Let's talk about ATI. And to be clear, this is not a retrospective on graphics card, even if I really like my old ATI Reg. Now here we are talking about any trajectory instruction, a paper released last week by Biden's research. This framework lets you draw trajectories on any image and turn them into realistic video motion. The magic is in how it unifies all types of motion control. You can move objects, create local deformations like fabric waving, or define complex camera movements. You simply draw where things should go. The key innovation is a Gaussian-based motion injector. Here's how it works. You draw key points and their paths on the first frame. ATI then encodes these trajectories using special Gaussian distributions, essentially creating smooth motion fields in the latent space of the video model. What's clever is that this motion injector is lightweight and plugs into any pre-trained image-to-video model. There is no need to retrain the entire backbone. During inference, it samples features at each key point location and propagates them through the entire video using bilinear interpolation. They've released the ATI 114B model, which is great since it is one of our best open source video models at the moment. The code and model are available with Apache 2 license, and the great Kijai has already integrated ATI into ComfyUI as part of the One Video wrapper. So without further ado, let me show you what you can do with it. First of all, make sure you have everything installed before starting. So go into your manager in Custom Node Manager. You want to make sure you have the latest version of the One Video wrapper from Kijai. We also want his Kijai Notes Pack, which is this one. And lastly, we're going to be using the Video Helper Suite. So make sure this one is installed as well. Once you have all of that, please grab the example workflow, which is included in the description of this video, and load it into your scene. So this workflow is based on the 1.2.1 image to video workflow from Kijai. At the very top, we have the section here about the models. We do have here the sampler, the prompt with the text encoder. Here is the output. It's a lot of node, but it's just to do some multi-view output with some extra information. So don't worry too much about that part. Here we have the image input. In that part in yellow, we're gonna do all the motion input. And here we're gonna say how strongly we want the motion to influence the generation. So let's start with the model. You will want to make sure you have downloaded the ATI Safe Tensor. So if you don't have it, please go to the Hugging Face link, which is here, download it, and save it into your models, diffusion models folder under ComfyUI. I'm using the Cosbit LoRa. That's purely to speed up my iteration process. And then I do have torch compile and block swap enabled to make sure my generation are not too slow and they also don't run out of memory. Those are specific to my own hardware and environment, so please make sure you adjust those according to the machine that you're working with. Here in the prompting, I'm not using any prompt at the moment, and we might keep it that way for now. Just want to see what the model is doing purely with the input from the motion without any additional prompt. In terms of the image input, I'm using a picture of Pétanque, which is a French game. It's going to be useful to really see how we can control individual element and see how the model deal with it. This image is also included in the description if you want to use the same one. I'm resizing it in AFK. This is purely to speed up my iteration process. One thing worth noting is that ATI only supports 81 frame at the moment for generation, which is the standard for 1.2.1. So don't try to reduce that number. As a reminder, 81 frame, it is 5 times 16 frame because the 1.1 works at 16 FPS plus one extra frame, which is the first frame of the input. Okay, so that's 5 seconds total. So keep it to 81. If you reduce that number, you're going to run into errors. Here I haven't added anything yet. I'm going to do that in a moment. In terms of the control for the ATI tracks, we'll tweak the settings in a second, but we're going to be able to adjust the temperature, how precise or how diffuse we want the effect on the generation. The top K, it's going to say how many points, how many motion points we want to use to control our image. And then the start and end percent. Do we want to affect the motion through the entire diffusion process or stop it halfway? As a reminder, at the early stage of the diffusion process, so the closer we are to 0, we are working on large-scale feature. And then the closer we are to 1, we're working on finer details. In terms of the sampling, I'm using 5 steps, which will be fine for most of my testing today. But when we are going to be trying to generate some final quality project, we definitely want to increase that number. At the moment, I'm just keeping it low to speed up my iteration. CFG, I keep it at 1 and Shift at 5. And then I'm using InPC as a scheduler. Now we're going to start creating the node that we need to redirect the motion. So we're going to go at the bottom of the workflow and we're going to look for a spline editor. So the spline editor, we're going to connect the background image input into resized image. And we are going to grab the output, like coordinates, and feed that into that node here. And that's going to go right into our ATI tracks visualize. This one is purely a helper to allow us to see what the motion is doing. And then we're also going to feed that into the motion control. And at that point, we're going to say how much of an influence we want to have. And then we have another track visualize here for our final comp. Okay, in the actual spline editor, we want to create a new canvas. So it's going to give us a curve. And we want to make sure that we set the point to sample to the number of frames that we have in our video. So I told you earlier that we were working with 81 frames, and that's assuming 16 frames per second. So 5 times 16 plus 1. However, for ATI, we need to work at 24 frames per second. So it's 5 times 24 plus 1, which is going to be 121. Let's run that graph. If you look here in that preview, you see the input motion that we've just generated, which is just a curve going around the frame. And then that's what's going to be fed into our solver. Let's tweak a bit that curve for a moment. Let's set that to path because we are going to create some path for our object. And we are going to just create a simple, like a straight line to start with. Up. And we are going to enable that final video combine node so we can pull on the entire graph and test that generation. I'm not going to make you wait for it, so I'm going to speed up the video and see you in a second. The generation is not too long, it's just under 2 minutes. And as you can see, this is the input image that we used. This is the visualization of the ATI controls that we've created. And this is a final video, and this is a final video with a control. If we're just doing one curve from left to right, we are creating camera motion from left to right. Okay, so you can obviously tweak that arrow to go in any direction that you want. We are going to create a few more to see more complex motion. So let's add another one. I'm using Control-Shift-V just so I paste while keeping the input connection. And now I'm going to do some circular motion. Up. We can do a bit more fancy camera motion here. just going to go in circle. Now I do have those two splines that I need to combine together. So I'm going to use append string to list. And then I'm going to take the output from the first one that goes into string 1, the output from the second one that goes into string 2. And we are going to bring that into our connector here. Now I'm going to run that. I can see here again the preview of my ATI tracks, and then we're going to see the generation in a second. And as you can see, we are rotating around the balls. You'll see that when I'm starting to do motions a bit more extreme, I am creating some artifacts, like some balls are starting to disappear. However, don't worry too much about that. If you do increase the number of steps here, you will be able to resolve those effects, and it should be more stable. Okay, continue to play with a few more motions just to give you an idea of what you can do. Let's add an additional curve. Okay, so I now have 3 different spline editor, and they all get combined with each other with append string to list, and then it finally goes into that final node here, and then into our control and our visualization. Okay, so now I'm going to do some zoom in and zoom out. Let's go from the inside to the outside. And if we do launch that generation, now it should do a zoom in. And as expected, we are now zooming on our game of pétanque. Now you can obviously do the opposite motion. So if you are reversing your arrows to go in the other direction, and you launch that one, you should be able to do a zoom out. As you would expect, you now have a zoom out. So feel free to experiment with more curve combination to create different camera motion. That should work nicely. Now let's start looking into object motion and explore the influence of the different parameters from the one video ATI tracks. So let's only work with one spline for now. So I'm going to take the coordinate string and plug it into that node here. Actually, you know what? I'm going to create a reroute. That would be easier to work with than my connector here. Let's do that instead. And blast that guy. Sweet. Okay. Take that curve, and we are going to do a sharp turn. So let's change the interpolation to linear. Let's run the generation. So we now only have one curve that is starting from the red ball and doing a sharp turn to the right. Because there is only one track, the models think I'm doing a camera motion. So now what we need to do is we need to pin the ground, so only the balls end up moving. And to pin an object, we need to add another spline editor into the mix. So we're going to use that append string to list and plug that one into our reroute. So now we're using the first one and the second one. And for the second one, instead of drawing an arrow, we are just going to create a point. So we put all the controller from the arrow the same spot. And we are going to run that generation. So if you look at the visualization that we have here, we have our main tracks that goes to the top and to the right, and then we have a static point on the ground to say we don't want the ground to move. So if everything goes well, the model should understand that what we are trying to move are only the balls. So if we look at the generation now, the ground is static and the balls are moving. You can see that the small white ball is not moving, and that's because the model at the moment doesn't recognize that as an individual object. And the green ball ends up moving, but part of it is being left behind, which is an artifact. That should be resolved if we were to increase the number of steps on the generation process. I'm not going to do that now, just to keep our iteration quite fast. Let's add another track. So I'm going to include that last one here. I'm going to put that one to linear as well. And I'm going to run the generation. So now we ended up creating a circular motion because we have two motion fields going in circle, and some balls end up being affected by one and the others by the other. As you can see, there are more artifacts into the generation because in the middle, some balls don't really know in which direction to go, and because I'm only working with 5 steps in the sampler, that's not enough to resolve the complexity of the motion. So again, we could increase the sampling steps if we wanted to have a nicer result, but I'm not going to do that right now. So let's look at the settings. So at the moment, we are working with a temperature of 220. The temperature is going from 0 to 1000, and it has an exponential fall-off. So there is more changes between 0 to 150, 220, and then the closer you go to 1000, like the less it changes. It does affect the motion field, and the smaller the temperature, the broader, the more diffused the field is, and the higher the temperature, the sharper the field, okay? So if we create a test and we bring that number to 20, I'm going to update my notes here, set that to 20 for future reference, so I know what the generation was. And I'm going to copy that one on the side, so we have it for reference. And for comparison, I'm now going to generate a version at 950 and update my text to 950. I often try to avoid very extreme value, like if you go to temperature of 0, 1000, because you might run into artifacts. And if we sync the preview, so it's easier to compare everything. Now what you can see is that when we are increasing the temperature to very high value, we have less of the smearing happening on the balls because the field is so much sharper around each ball that the model is able to create some nicer motion at using less steps. If the temperature is quite low, there is a lot of overlap of motion field, And so the model is struggling to resolve that with just 5 steps. Okay, so we need to increase the number of generation to do that average of motion field for the individual balls. Now, another setting that we can play with is the n%. So let's try maybe a value of 0.3 and see what we get. And copy that one on the side for comparison. So the start person and end person, that affects the diffusion process. So remember that at the moment I'm working with 5 steps. So we're saying for each frame that the model is going to generate, when are we going to influence the generation with the ATI tracks motion? If we're leaving the person to 0 to 1, we're going to influence it at step 1, step 2, step 3, step 4, and step 5. If we're setting that to end at 30%, we're only going to influence it for the first step, okay? So if we were saying that n% should be at 50%, so it would be 50% of 5, so it would be 2.5, so we would be influencing the first and the second step. So if we look at the result, it's quite subtle, but if you look closely, especially at the end here of the process, you can see that the red ball is jittering quite a bit around the tracker. And if you look on that version here, the motion is more linear, like it follows the tracker better. And the reason being, in that case, we are pushing the motion at every step of the process. And on the left case here, we stopped doing that earlier in the diffusion process. So there is more freedom for this model to create something. And here we are controlling the model quite tightly. Another setting that we can explore is K, and that's also something that's quite subtle. So I'm going to change the input motion so we can see it better. What we're going to do is we are going to create 2 different motion, one for the red ball. Let's go this way. Make sure this is properly linear. Create a motion for the orange ball, a different direction. I want to have 2 contradicting motion so we can see how it's going to influence the surrounding balls. Now, so far, I kept all my motions to 121 frames to the full 5 seconds. So everything is happening across those 5 seconds. So that motion is going to start here at the beginning of the generation and end here at the end of the 5 seconds. In that example, I'm going to reduce it to about 60 frames. Remember, 60 frames at 24 FPS, so that's about 2 seconds. And that's going to make sure that that motion is a bit faster. Let's start with a top K of 1. Let's go back with quite a broad temperature. Okay, so lower value. And let's run that generation. So we said temperature 50, top K of 1. And we've put our n%, I think, back to 1 for the case. No, we didn't. Let's do it. And let's run the generation. Okay, and now let's do a comparison where we're now going to increase the top K to 2 and see, hopefully, some difference. It's quite subtle again, so hopefully we can see a clear difference between those two generations. So if we sync the preview to make it easier for us to see, what's happening is that if we look at the blue ball here, it doesn't move in the case of, oh, I forgot to update the top key here, it should be top key of 2. It doesn't move in the case of top key being 2 because it is confused between the two motion fields, okay, this one and this one. But in that case here, where top key equal 1, where we're saying, no, it's clear we only want to be affected by one motion field, then it's clearly moving in that direction. So as I said, top key and start end % are quite subtle changes. It might pay off to keep default setting most of the cases, and then if you're trying to get something quite specific, like if you want to have some softer motion, you might want to try to increase the top key if you want to average multiple control fields together. And then if you want something a bit more realistic, where you want to let the model do its own work as opposed to constraining it too much, you might want to start reducing the end %. Now that we've done that, let's look at another example where we would direct a bit more the motion of the different balls here. So what we're going to do is we are going to create quite a few more of those curves and create all the different arrows for them. So I would like to have 2 different motion for different balls at different speed, and then I would like to make sure that all the balls that are not supposed to be moving remain static. I'm going to create a lot of different lines, and I'm going to speed up the video so I'm not boring you too much, and then I'll talk through it in a second. Okay, let me kill that one for a second. Let's bypass that node so we don't pull on the whole graph. And let's run the preview to see what's happening. Okay, so what do we have here? We have 2 different balls that are supposed to be moving, the green and the red. And then we have all those balls here that are being pinned. I'm not going to put a pin on the small white check because it's not moving anyway at this stage. I messed up some of the timing, so let's fix that. This arrow is set to 121 frames, that's fine. The pin of the ground is 121 frames, that's fine as well. We want it to remain static for the whole shot. This arrow here set to 60 frames, can try to reduce it a bit further, maybe go to 40 frames to have faster throw. For that one here, for the static balls, I'm going to put all of those to 121 frames for now to make them entirely static. 121, 121, 121, 121, and 121. Check my settings. I'm going to go back to the default temperature of 220. Top K can stay at 2, percentage 0 to 1, that's fine. Update it here. Say 220, top K at 2, and we are going to run the generation so we have something to compare. Okay. We have our static balls that remain static because we set them to be static all the time, and so they don't interact with the other balls that are currently in motion. The first thing I'm going to do is I'm going to delay the red ball. So at the moment, both the green and the red one are being launched at the same time, and you might be facing a situation where you actually don't want objects to start moving from the first frame of your shot. You might want them to move halfway through the shot. So how are you going to do that? you need to have the track being created as the first frame of the shot. You cannot create tracks halfway, but you could have them being static for maybe 30 frames and then start moving after that. Let's turn off that, bypass that node for a second. So if we look at the arrow of our red ball, which is that one, what the spline editor is doing is that it is generating a bunch of coordinates, and that's what's being fed as tracks into the model. And those coordinates are just X and Y value over time. If you look here, you get the first object for the first frame, coordinate X and Y, then coordinate X and Y for the second frame, and so forth and so forth. What we can do is that we can edit that line here, and we can add more points at the beginning, okay? To make that easier for us, I mean, you could also try to make it work with the arrows and let it update the point automatically, but it's going to be very challenging to get specifically what you want. So what I would suggest you to do is to do some string addition if you want to do that. So let's use multi-line string constant multi-line. And we are going to copy the first set of coordinate. Okay, so this is the first point, X and Y. If you look into your shell, up, here, you're seeing the output from the spline editor, and you're seeing all those coordinates, which are the same that I have at the moment here. I have plenty of them because I have a lot of spline editors in my scene. If you look at the syntax that is being used, we have two square brackets at the beginning, and then it finishes with two square brackets, okay? So what we need to do is we need to make sure we have that, and we have that at the end, okay? Now, if I were to do that, that would only be one frame. I say I wanted to have more than one frame, so I'm going to add how many as you want for those, and they're separated by comma. So I'm just gonna add a few, and say maybe 30. Hope doesn't have to be accurate. This is just for testing at this stage. Okay, you add a few of those, and you remove the comma at the end. And I'm going to remove the end bracket as well because I'm going to concatenate with the other part of my string. I'm gonna have that one here. Now I'm gonna take the output of my spline editor that used to be fed into that node. And before we do that, we're going to concatenate it with that one, okay? So we can use concatenate node, and that node takes two strings. So we can take our first string and we can take the second string and then bring it back here. Now we need to make sure that the strings are properly formatted. We say that we need to start with two square brackets and close with two square brackets. And the output of that node is already a string starting with two square brackets and ending with two square brackets. So I need to edit it. So let's use a replace node here. So we're going to take that one and feed it into our concatenate. And before we do the concatenation, we're going to remove the two opening square brackets and replace it with nothing. So we're going to basically remove them. And here, through the concatenation process, I'm going to use a comma as a delimiter. So what's going to happen now? We're going to concatenate a string that starts with two square brackets that has a bunch of static coordinate, doesn't end with a comma. Then we're going to add the comma to it. And then we're going to take another string, which is coming from the spline editor. We're going to remove the opening square bracket because we're already halfway through that list, and then concatenate it with the previous one. And then at the end of that string, there is already the closing bracket, so we don't need to add them back. I'm gonna try to run that. And now what do we see? We see that here, that balls remain static for a bunch of frames and only start moving after a while. While we're here, we're gonna make this motion a bit faster because they are very slow at the moment. So we're going to reduce that pointer sample maybe to 26, and same here for that one. Instead of 121, we're going to use something smaller, maybe 40. Let's render that. Okay. Feel free to play with those values. Keep in mind that the faster the motion, the harder it is for your model to solve it without artifacts. So you will need to increase the number of steps for the model to properly resolve it. But if the motion is very slow, it's going to look slow motion. So that might or might not be what you want to generate. Another thing we need to do is making sure that those balls here start moving when they are being hit. So here we do have the blue ball, which is here, so there is a pin on it. So let's look at the number of points that we have here. So we had 40 frames, so 40 points to go from here to here. So let's turn off the pin at frame 40. And now we need to do the same thing with this one and pin the orange and the red, because this one is likely to collide with that one. And here we add 26 frames plus all the line from here. You can count them if you want. Okay, so we had about 55 lines here. So that's 55 frames plus 26. So that's 61, 71, 81. We are going to take our orange ball, 32, 81, and the red ball as well, 32, 81. Okay, so now if we rerun that preview, we should see that on impact, this one being unpinned and those two are being unpinned. Okay, so now let's run that generation and see what we get. So we see a bit of motion, but there are still some obvious problems of balls going through. So let's refine a bit our path. And I mean, if we look at what's happening here, I think one of the biggest problem is that we are bringing our red and green balls too close to the other one. Okay, so we are creating some interpenetration effect. And so then we end up with the model not being able to resolve the collision properly. So what we're going to do here with that arrow, we're going to stop it earlier. Up. Same here. We are also going to change some of those timings. Because we made the arrow shorter, now it's going to be moving slower, so we're going to reduce the number of points to make it faster again. Actually, this one should still be pretty good. And we are going to change when the blue, the orange, and the red balls are being released, so we release them a bit sooner. So to make sure there is enough time for the collision to happen. So if we grab our blue ball, that's releasing at 40 right now. Maybe we try to bring it down to 37. And then for the orange and red balls, they're releasing at 81 right now. Let's see if we do 68. Remove quite a few. Let's have a look. Without doing the generation, just look at the timing of things. Okay. Let's try that one and see where we land. So we have some interesting swallowing effect. One thing that is worth doing when you start refining some of your motion is to start putting a prompt. That will help the model understand what you're trying to achieve, and that will help guide the generation. So let's say a green and red rigid. Plastic balls rolling on the grass, colliding with colorful plastic balls. I'm also going to increase the temperature to a higher value, just so we have something that is more focused on the ball that we're trying to move. So trying to tighten our motion field. That's temperature. Just add it here into the note for reference for later. And I'm going to launch the generation. So we've improved a bit a collision here, but here it's still struggling quite a lot. At some point, we need to increase the number of steps, and so we can't stay at 5 steps forever because the model is going to struggle to resolve what we have to resolve. So let's try that to go to 15 steps and launch the generation. And we finally have some nicer collision without any penetration. One last thing we can try just for comparison is to, if we put this on the side, it's to reduce the n% value. So let's bring it to 0.2, which will be just above 2 steps, and see how that changes the behavior. Yeah, the change is quite subtle between the two. Technically, the one on the left, which is the one with n% reduced to 0.2, should be a bit more natural because we're leaving more freedom for the model to do the generation. But yeah, it's all subjective. Anyway, that was a surprisingly difficult exercise, and even if the original image it seemed quite easy at first glance, but I really wanted to use this exercise to show you all the different parameters and how you can work with that ATI model. There was no way to cheat here, so we really needed to analyze each parameter and find the right settings for it. So have a play, try to run it on different type of picture, try to create different type of motion for either animals, people, or camera. It should work with everything. The scene is available in the description, so feel free to start from that if that's helpful. Remember a few things that we learned today. You will need to increase the amount of steps, especially if you're dealing with very fast motion. Otherwise, you're going to run into artifacts when the model is struggling to process the motion that you're inputting into the generation. Try to add a prompt that will help guide the model in addition to your motion control. Keep the temperature higher if you want to focus the influence on a specific area, or keep it lower if you want to have a broad effect, like dealing with camera motion, you might want to have a lower temperature. Reduce the n% if you want to let the model have a bit more freedom with the generation. And then you can always tweak those curves, reduce the points of sample if you want to make faster motion, or increase them if you want to make slower motion. Remember that this is working at 24 FPS, even if the server itself here is working at 16 FPS. And you can always use a string constant multiline to offset the beginning of the motion, so to add multiple static points ahead of your coordinates that are being generated with the spline editor. Have a play, share with us what you come up with, and don't hesitate to ask questions if you have any. Thank you for watching. It was a pleasure spending that time with you. As usual, you'll find all the links and the workflow in the description below the video. If you learned something new today, please like and subscribe. And don't forget to share your experimentation or any question you might have in the comments. I'm looking forward to hearing from you, and I will see you next week for another episode of AInVFX News. Thank you for watching.